Okay, good morning everybody. Oh, you guys can't see the thing, can you? Now you can see the thing. Okay. So, last two classes we've been talking about U-substitution. First we talked about doing U-substitution using indefinite integrals, where the result of our work is a class of functions. Next we talked about how to use U-substitution with definite integrals. Okay, and when we talked about using U-substitution with definite integrals, there were sort of two schools of thought, or two methods which you can use. You can leave the bounds in terms of x and work through the entire problem and then switch back to x and then plug in. Or you can do a little bit of work up front and change the bounds to be in terms of u, and then just finish the whole problem with u. Whichever method you use on a homework or on an exam is totally up to you. I'll never ask you to use one method over the other. But there will be times where it'll be much easier to use one over the other. For example, let's see here. If it's really annoying to say, let me highlight in yellow here. So here was where we kind of, hello? I can't highlight here for some reason. Okay, well, right here was where we kind of plugged in our bounds into the function u equals negative x squared to get our new bounds. If the function u was extremely complicated or our numbers were really bad, it might be kind of painful to do that plugging. But generally, these two methods are going to be more or less the same amount of work. Some calculus students do prefer using method 1 just because it stops them from falling into the very common mistake of accidentally plugging the x values in for u in the u. So let me draw your attention now to this part right here where we have negative 1/2 e to the power u evaluated at x equals 0 and x equals 1. The really common mistake that I see calculus students make all the time is they'll write 0 to 1 instead of x equals 0 to x equals 1, and then they'll plug in 0 and 1, and they'll get the wrong answer because those were x values and they plugged it in for u. So that's a common mistake that you should try to avoid if you can. Okay, so what I'm planning on doing today is I actually somehow managed to get myself ahead of schedule, which is great because now I get to spend today doing a bunch more examples. So a lot of people in their exit slips have been posting, I want to see more examples of this type of problem or that type of problem. Usually I have to just say, well, I'm sorry, I can only spend so much class time on examples. Please come to office hours. But today we'll actually do a bunch more examples. So as we're going through some of these, you guys can sort of rack your brains and think about what you might want to see more examples of, and if you come up with something during the lecture, then maybe I can find a problem for you. Okay? Sound good? Okay, so let's start with this problem, problem number 4. So we have this integral. It's the integral of 2x times x squared plus 4 dx. And we're asked to find this indefinite integral in two ways. So notice that we don't have any bounds here. Okay, we don't have any bounds, so this is an indefinite integral, so we should get a class of functions at the end. Okay, or a family of functions. And there's two ways that we can do it. The first way is to use the U-substitution, u equals x squared plus 4. That's valid because what's being multiplied out front is the derivative of u, and then out back is dx. So our leftovers kind of exactly match up with what du should be if we pick u equals x squared plus 4. So that's nice. That's one way we could do it. The other way we could do it is just to distribute, right? We could distribute this 2x squared onto this 2x onto the x squared and the plus 4. And we'd have a polynomial, and we could use linearity of the integral to just find the antiderivative of each piece of the sum, and then we'd get our answer. So those are the two ways that we're going to do. So let's do way number 1. So I'm going to let u equals x squared plus 4. Then, well, du dx is going to be 2x. Therefore, du equals 2x dx. So I can rewrite this integral. Let me do what I usually do. I'll point out what's u and what's the leftovers. So x squared plus 4, that's u. And then my leftovers are 2x dx. And that's exactly what I have on the right-hand side of the du equation, so I don't need to do any funny business playing around with constants. It just kind of worked out. So I can rewrite this equation as the integral of u du. And I know if I do that, I'm going to get u squared over 2 plus c. And remember, if we want to use U-substitution and we're doing an indefinite integral, we're looking for a function of x, right? If we do the integral of 2x times x squared plus 4 dx, our answer should be in terms of x. It should be some function of x. So let's switch back now to x. I'll plug in x squared plus 4 for u, and I'll get x squared plus 4 over 2 plus, sorry, that should be squared, plus c. Are there any questions? Let's have some thumbs. How do we feel about that U-substitution? You feel like you could do that on your own? Thumbs up if you think totally could do that on my own. Thumbs down if you're like, I don't know about that. Okay. I'm seeing several thumbs up, some thumbs sideways. We'll do some more U-substitution practice. Hopefully it'll become more clear. Okay, let's do it the second way. Okay, way number 2 here. We're supposed to use distribution and then anti-differentiate. Okay, that just means find an antiderivative. Okay, so we'll rewrite the integral where we will distribute this. We'll get 2x cubed plus 8x dx. Okay, and now all we have to do is find an antiderivative for each of these pieces and then add c and we're done. So 2x cubed, we'll raise the power from 3 to 4 and we'll divide by the new power. We'll get x to the 4th over 4 plus, let's see here, 8x is going to become, we'll raise the power from 1 to 2 and divide by the new power. So 8x is going to become 4x squared. And then we'll add c. Okay, so in this case, it was, I think, somewhat easier to just distribute than to use U-substitution. Certainly took a little bit less writing. When it wouldn't be convenient to use this method is if, for example, instead of doing this integral, we had something like 2x times x squared plus 4 to the power 9. Then it's going to be really, really painful to FOIL 9 times and then multiply all that by 2x. Okay, so if you had something like that, you would definitely want to use the U-substitution method. But for just one power of that term, it's not too bad to just distribute. Okay, and now we're supposed to explain how the two answers we found are different. Are they both correct? Let's start with, are they both correct? Seeing heads nodding, meaning yes. So yeah, they are both correct. Are they equivalent? Yeah, because if we foiled this, x squared plus 4 squared, or x squared plus 4, all quantity squared over 2, let's do it. If we foiled, we get x to the 4th plus 16x squared sorry, what am I doing? X to the 4th plus 8x squared plus 8x squared plus 16 over 2 plus c, and that would be equal to, something's gone wrong. I made a mistake here. When I raised this power to 4, it should have become 2 times x to the power 4 over 4. 2 divided by 4 gives us a 2 in the denominator. Sorry about that. Okay, so we get x to the power 4 over 2 plus 8x squared divided by 2 becomes 4x squared. And then I've got plus 8 plus c. Are these two things equal to each other? X to the 4th over 2 plus 4x squared plus 8 plus c. Is that equivalent to x to the power 4 over 2 plus 4x squared plus c with no 8? This is the key thing here. This 8 is missing on the right-hand side. Kevin's nodding his head yes. You want to explain why?
Because the last c on the left problem could equal 0.
Yeah, so we can absorb the number 8 into our constant, basically, is the way that it's going. So this left-hand side reads like, take the function x to the 4th over 2 plus 4x squared and then add the number 8 and then add some other number. Whereas the right-hand side reads, take the function x to the 4th over 2 plus 4x squared and then add some number. Well, adding 8 and then some number is the same as just adding some different number. So we can just absorb into the constant term. So these two things do mean the same thing. Okay, each side is referring to a family of functions. Okay, questions about problem number 4? Perfectly clear? Okay, today's the day to ask questions, so if you have questions, please do ask. All right, we'll do this next problem, which I kind of punted the last time we were in class because we were running out of time and I didn't want to go through the pain of explaining how this is going to be a little bit tricky. In fact, this question is not worded super well. I'm gonna say total area between this function and the x-axis. Between x equals -1 and x equals 1. I'm going to star this because this problem should be rewritten by my overlords. Okay. Find the total area between this function and the x-axis when x varies from -1 to +1. Okay, so we have some function x over x squared plus 1. And the reason that I rewrote this problem in this way is because if we were to look at the graph of this function, well, the denominator is x squared plus 1. No matter what number we plug in for x here, x squared will be a positive number, and then if we add 1 to it, we'll have still a positive number. However, the numerator, x, is going to at times be negative and at times be positive. Okay, so we're going to have something that looks really funky, but it might look something like, let's see, x over x squared plus 1. When we're at -1, it'll be like -1/2. And then when we're at +1, it'll be like 1/2. So it's going to look something like this. Okay, so it's a little bit misleading to ask find the total area under this function because, well, some of the function is beneath the x-axis, so we're going to need to count this as a negative area. Okay, however, the way that the question is now worded is it says find the total area between this function and the x-axis. Okay, and this is a type of question that I want you to be aware of. It actually cropped up on a homework problem, which I later removed because we hadn't talked about it in class. Okay, and the reason is if we want to find the total area, okay, if we want to find the total area between the function and the x-axis here, what we're going to need to do is not take the green thing and subtract from it the red thing, the red area. We're actually going to need to take the green area and add to that the red area. Okay, so we're going to have to be a little bit clever here. Okay, what I really need to do for a problem like this is take red area as a positive number and add the green area. Okay, that's what I need to do. Take the red area and add to it the green area. Okay, here's how I'm going to do that. I know that if I just take the integral from -1 to 1 of f of x dx, that's going to give me the green area minus the red area. Okay, so the trick that I'm going to use here is to say, well, the integral from -1 to 1 of f of x is the same as the integral from -1 to 0 of f of x dx plus the integral from 0 to 1 of f of x dx. Okay, where this first part represents the red area as a negative number. Okay, so what I want to do now is modify this so that I'm not taking the red area as a negative number, but taking the red area as a positive number. So I'm going to take this first part of the integral, and I'm going to negate it. So I'm going to write, instead of this, so this is not quite what we want, I'm going to write instead the red area. If I really want to know what the red area is, it's negative integral from -1 to 0 of f of x dx. And then that will be the red area as a positive number, because it should be this integral will give me a negative number, so if I take the negative of a negative number, I'll get a positive number. Then I'll add the green area, which will be the integral from 0 to 1 of f of x dx. Okay. So I am going to white out this part here so I have more space. They just never give me enough space. Okay. So now let's actually do this. Okay, so first of all, okay, let's put the pen back. First of all, I'm going to let u be equal to x squared plus 1. Then du dx is going to be equal to 2x. So du is going to be equal to, this means that du is going to be equal to 2x dx. So what I have is the integral of f of x. Now f of x is x over x squared plus 1, which looks like 1 over u, where the u is the denominator, and my leftover is going to be x dx. So I need to solve the right-hand side of this du equation to look like x dx. So I'll move the 2 over to the other side, 1/2 du, that's what x dx is. So I can rewrite this integral as the integral from and I'm going to leave this, I'm going to use method 2 today. I'm going to leave the bounds in terms of x. So I'm going to make sure to write x equals -1 and x equals 0. And this is going to become 1 over u times 1/2 du. That's negative, and then I'll add to that the integral from x equals 0 to x equals 1 of 1 over u times 1/2 du. Same u substitution being used for both integrals. I'm going to pull the 1/2 all the way out front. And the integral of 1 over u is just going to become ln of absolute value of u. We're going to evaluate that at x equals -1 and x equals 0. And that should be negative. And then we'll add to it ln absolute value of u, evaluate that at x equals 0 and x equals 1. Okay, so let me just point out really quickly that this 1/2 here, from each of these two pieces, it came out front, and I put these parentheses around here. I just took out a greatest common factor. Okay, I took the 1/2 out of both integrals and put it out front. Okay, so nearly there. Since I'm using method 2, and I have x values, but a function of u, I need to make sure to switch my function u back to a function of x before I plug in. So I'll keep my 1/2, I'll keep my parentheses, and then this will become negative ln of absolute value of u was x squared plus 1. x squared plus 1, evaluated at x equals -1 and x equals 0. And I'll add to that ln of the same thing, x squared plus 1, and I'll evaluate that one at x equals 0 and x equals 1. So we'll get 1/2 negative ln of, first we plug in 0, we get 1, and then we will subtract, but since there's a minus sign, it means we'll add ln of, now we plug in -1, we get 2, and then we will add to that, where we plug in 1 first, so it'll be ln of 2, and then we'll subtract, when we plug in x equals 0, we get ln of 1. Now who can tell me what is ln of 1? Can we evaluate that right away? If I do ln of 1, what do I get? Not 1. If I do y equals ln of 1, the corresponding exponential equation would be, if I raised both sides to the e power, it'd be e to the y equals e to the ln of 1. Remember, e and ln are inverses, so the right-hand side would just become e to the y equals, the right-hand side would become 1. So if I take e and I take it to some power and I get 1, what was the power? 0. So ln of 1 is 0. So what am I left with? 1/2 times 2 ln of 2. I get ln of 2. Okay, so this is just something that I want you to be aware of. Sometimes they will trick you and ask, well, what is the area between the function and the x-axis? And then we have to be careful to make sure that we count any area beneath the x-axis as positive area, which is a departure from our understanding of integration, which counts area beneath the x-axis as negative. Okay, so we have to take any part of the integral which lies beneath the x-axis, we have to negate it in order to count that area as positive area, as opposed to rather when we have something like this green part moving left to right, it's kind of like we're accumulating area, right? But if we were to then pass beneath the x-axis, then this part here would be, well, the opposite of accumulation. It'd be going away, right? We'd be subtracting area as we move to the right, okay? Because more and more area would be beneath the x-axis. So we have to be careful and kind of treat this in a special way. Ryan, do you have a question?
Yeah, when you added and subtracted the 4 ln's at the second to last part,
Mm-hmm.
how do you know when to add and when to subtract? Like
So,
the last line.
on the second to last line, so you're talking about this line.
Yeah.
So that came from the fundamental theorem of calculus. So let me trace my steps, and I'll show you in pink. So I had a negative sign here and then an integral, okay? So I kept that negative sign, and then I did the integral. So I took the antiderivative, okay? So this negative sign is the negative sign, and the thing in the box is the thing that I circled. Okay, so that's the antiderivative where we plug in -1 and 0. So then I kept the negative sign again, and I just replaced u by the thing that's equal to u in terms of x. And then I kept my negative sign again. And then what was inside why don't I write an extra line here? Ooh, that's not going to work, is it? No, that's not going to work. Okay. What I really did here was maybe I should have had an extra line in here to make it super clear. That negative sign stayed, and then I had a big parentheses where I do this thing in the box, which is ln of, we plug in 0 first, 1, and then minus ln of, we plug in the second thing, which was negative 1. That gave us ln of 2. And what I did in one step here was I actually distribute this negative sign here. So then we would have plus the other integral. Okay, so when I distributed this negative sign onto the ln1 and onto the negative ln2, it became negative ln1 plus ln2. Does that make sense?
Yeah.
Okay, and then I had the plus sign. This plus sign just came down the whole way with us, plus, 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 plus. And then everything that's in these orange brackets came from doing this plug, okay? So we had to evaluate ln of x squared plus 1 at positive 1 and 0. So we plugged in 1 first, that's how we got this ln2. And then we plugged in 0, that's how we got this ln1. And we should subtract them because the fundamental theorem of calculus says integral from a to b of f of x dx is just going to be capital F of b minus capital F of a. Where capital F is the antiderivative. Did that fully answer your question?
Yeah, it did. Thank you.
Is anybody else confused about the work I did for that problem? Did you guys think that was a hard problem? I thought it was somewhat challenging. I think the main challenge really was in looking at this function f of x and realizing that some of it lies beneath the x-axis, and so we have to be very careful about what happens here. Because guess what? If we had just done the integral from negative 1 to 1 of f of x dx, we actually would have gotten 0, because those two areas are actually going to cancel each other out. They're symmetric. That's what we call that. Okay. I think that's all I want to say about problem 5. Are there any lingering questions about that one? Okay, if not, then I'll keep going. I'll just do this last one here, and then we'll do maybe 1 or 2 from another section. So this will be the last U-sub problem. Okay, so we want to find the total area underneath the function f of x equals 3x squared e to the x cubed. Now let me ask before I start. If x is between 0 and 1, is there any part of this function which lies beneath the x-axis? Are there any x values between 0 and 1 such that when I plug them into the function f of x I get a negative number? That's my question. Yeah, the answer is no, there's not, because this 3x squared part will be 3 times something squared. If I take any number and I square it, I get a positive number. So 3 times a positive number is a positive number. Then I take that positive number and I multiply it times the stuff in the pink brackets, e to the x cubed. If I take e to some power, doesn't matter if it's positive or negative, it's always going to be a positive number. Because e to the negative 1 million would just be 1 over e to the 1 million, which is a positive number. Okay, so there's no way for me to plug in any number into this function and get a negative number. So I'm not going to worry at all about possibly having area lying beneath the x-axis. Okay, and as I should, because the question really lists find the total area under this function. Right, so if you read something like that, you should assume that the function lies above the x-axis. Okay. All right. So let's do it. We just want to do the integral from 0 to 1 of 3x squared e to the x cubed dx. I'm going to choose u to be equal to, what should I choose u to be equal to? Kevin? Very good, x cubed. And du will be 3x squared dx. And stroke of luck, we don't need to play with the constants, excuse me. We've just got 3x squared dx right there. And then u is x cubed, and that's just right here. So if we want to write this in terms of u, it should be the integral from, and why don't we use method number 1 here? We'll use method number 1. We'll change the bounds. So I'm going to take 0 cubed here, and I'm going to take 1 cubed here. And then we'll have the integral of, in terms of u, this is just e to the u du. And if I take 1 and cube it, I just get 1. If I take 0 and cube it, I just get 0. So this is equal to the integral from 0 to 1 of e to the u du. And I just want to point out that these values here, 0 and 1, they're values of u now. We changed them by plugging them in to u equals x cubed. We took those x values, 0 and 1, and we plugged them into x cubed. So I changed the bounds. They wound up staying the same, but functionally, I changed them. Okay, and the antiderivative of e to the u is just e to the u. So I'll evaluate that at 0 and 1. So I will get e to the 1 minus e to the 0 by the fundamental theorem of calculus. E to the 1 is just e, and if I subtract from that, what's e to the 0? Kevin?
1.
Yeah, just 1. E to the 0 is just 1. Okay, and that is the total area underneath this function. What does it look like? I'll draw you a quick graph. It looks something like this. Okay. Questions about that problem? No questions, huh? Okay. See how much time I got. I got 10 minutes. All right. I want to go back and talk about everyone's least favorite problem because it's a great problem. So many people wrote on their exit slip that they were not a fan of this problem, which means we should really talk about it some more. Okay, so what does this say? A runner's heart rate is changing at a rate of b of t beats per minute per minute. Okay, so b of t is measured in beats per minute per minute. Okay, beats per minute per minute. Okay, so what's graphed here is not heart rate, but the rate at which heart rate is changing. Okay? Now, we are asked a question about heart rate. So, the way we should read this question is, we are given a rate of change of a quantity, and we are asked a question about the quantity itself. That should get us thinking about integration. Okay? Because if you remember, we had a note box on this note set which said, where'd it go? Here it is. If a function is a rate of change in a quantity, then the integral from a to b of f of t dt is the total change in quantity from t equals a to t equals b. Okay? So the area under the curve is going to represent accumulated change. Okay? That's what we should be thinking going into this problem. Okay, so since b of t here is a rate, what we should be thinking is that as we move from left to right, the area that I am accumulating here is going to represent, since b of t is a rate of change of some function b of t, which gives us the beats per minute, then this area here, integral from 0 to 1 of b of t dt, is going to be equal to the total change in heart rate during, what is this, minutes? T is in 10 minutes since they started running. So 1 means we've gone 10 minutes. During the first 10 minutes. Okay? So, I think the reason that this is confusing is because the quantity which is changing is itself a rate of change. Okay, I think that's what's confusing. People don't like working with per minute, whether it's miles per hour or whatever. Meters per second squared. I think that bothers people. So, what we really need to do is just consider that we have a quantity. Beats per minute is measured as a number, so it's a quantity. And we are given a function which represents a rate of change of that quantity. So the integral from a to b of the rate of change is going to represent the total change in that quantity from a to b. So we are asked to answer the question, when is their heart rate the highest? When is their heart rate the highest? Okay, so the way we should think about this graph is at time 0, this is a runner? This is a runner. Okay, so at time 0, t equals 0, we start running. With an initial heart rate some number b of 0 equals to, we don't know what it is, c. Some constant. So we have an initial heart rate. Maybe they're a runner, they're in relatively good shape, their resting heart rate's like 50 beats per minute or something like that. Okay, so they start running at that time with a certain heart rate. And the area which we accumulate as time moves forward represents the increase or decrease in heart rate of the runner. Okay? So the way that this reads is we start running, and as we move from left to right, we are accumulating area. This means heart rate is increasing. Okay? And we continue to accumulate area up until this point right here, where we cross the t-axis. Okay? Once we cross the t-axis, then we're not accumulating area, but rather we are decrementing area. Okay, so the way we should read this graph is, as we move from left to right, we accumulate the area. Since this graph is a graph of a rate of change, if we want to say something about the quantity which is changing, we have to be thinking about integration. The graphical interpretation of integration is accumulation of area under the curve. So as we move from left to right, we're accumulating area, our heart rate is increasing. Okay, so let's see here. Yeah, this is rate of change. So, okay. What does this mean in terms of the problem? So we want to answer the question, when is their heart rate the highest? Well, that will be, since we start with a certain heart rate and then we immediately start increasing our heart rate by accumulating area, and we continue to increase our heart rate by accumulating area until we stop accumulating area. Our point of interest is right here. That's not a good color, is it? This is peak beats per minute. That's when we have accumulated the most area. Okay? Then after that, the runner's heart rate starts to change in a negative way. The rate of change of heart rate is negative, meaning that heart rate itself will be a decreasing function. You can see that by the fact that we're sort of accumulating negative area or decrementing area here. So then our heart rate decreases for a short time. Heart rate decreasing in that region until we hit the end point here. Okay. Oh, their starting heart rate was 80 beats per minute. I guess I shouldn't have used C here. So their starting heart rate was 80 beats per minute, and then they accumulated a bunch of heart rates here. And they even ask us to estimate their heart rate at that time if their starting heart rate was 80 beats per minute. Well, we can do that by taking 80 plus the integral from 0 to 3.5 of b of t dt. Actually, not quite. We have to be a little bit careful here. T here is measured in 10 minutes since they started running, meaning that each block here is 10 minutes. B of t is measured in beats per minute per minute. So if I go from 0 to 3.5 in terms of 10 minutes since they started running, then I should measure actually the integral from 0 to 35 of b of t dt. So this reads like, take our initial heart rate and then add to that the change in heart rate from time 0 to time 35. And what we're going to get is 80 plus whatever this area is under this curve here. So let's count some boxes. I count 1, 2, 3, 4, 5, 6, 7. These two together make 8, 9, 10, 11. These two together make 12. And these three together make 13. So let's see, the total area here is 13. Let's see, should we be thinking of these boxes as having rate? Oh, they're 5 high. So 13 times 5 would be 65. So this is 80 plus 65. Because the area of each box, no, they're not. They're 1/2 wide, aren't they? So the area of each box is actually 2.5. So this should not be 65. This should be 32.5. So our ending heart rate is like 112.5. Okay. Don't want you to focus so much on the actual counting of boxes and area. What I do want you to focus on is how to interpret the graph of a rate of change and its relation to the quantity which is changing. Okay? All right, we're done for today. If you have any questions, you can hang out after class. Or if you want to see the next part of this problem, I can show you that as well. On Friday, we'll do something new. I think a week from Monday will be your next exam. I think. Check the syllabus. It has the date on it.
The syllabus said that the exam was next Monday. No?
That's what I thought too.
Yeah.
Like this coming up Monday.
Are you sure?
I think so, yeah. It's on my calendar.
That's what I have written in my calendar, but I mean.
Well, let's check it really quick. That doesn't sound right to me, but let me look. Oops, that's the wrong folder. Let me go into getting started. Exam 2, Exam 3 is on Monday, November 16th. Dang, okay, so today's November 11th. Huh. Exam 3 is on Monday. Why did I think that it was... Okay. Well, I better make an exam then for you guys, a practice exam. I'll make it today. Okay, I'll send out an email to everybody about that.
Have a good one.
Yep, you too.